Yes, in my last class I discussed space vector PWM technique and hysteresis current control PWM technique. I told you that in space vector PWM technique, at any given time only one switch is being switched. Only one switch is being switched at a time. We used two active vectors and the zero vectors to synthesize the required space vector. For the sake of convenience, we divided the total zero vector time into two, and we applied 0, 0, 0 and 1, 1, 1. Okay, this is like this. See in this figure. See, assuming that we are in sector 1. Sector 1 is if theta is in between 0 to 60 degrees. So initially we are at the origin with 0, 0, 0. All upper switches of the inverter are off. So at the end of Tz by 2 period, okay, we turned on only the upper switch of phase A, okay, 0, 0, 1, okay. So vector V1 is applied for T1 duration, and at the end of T1 we turned on the upper switch of phase B. See, we did not do anything to the upper switch of phase A, it is still on. We turned on another switch, okay, and upper switch of phase C is still off. So it is 0, 1, 1. We call this vector as V2, and that is applied for T2 duration. And at the end of T2 we turned on the upper switch of phase C. See, all three switches are on. That is for Tz by 2 duration, and this entire duration is Tc, where Tc is the sampling period or the total sampling time divided by 2, or Ts is the period for which or during which the space vector is stationary, okay. Or see in this, it is 0, 0, 0 to 0, 0, 1, only one switch is switched. From there it is 0, 1, 1 and again 1, 1, 1, then again go back, same thing, whatever that happens here, it happens in this fashion. So at any time only one switch is being switched. I also told you that if all three phase voltages are sinusoidal, the locus of space vector is the circle. And what is the maximum value of Vs, or what is the maximum value of the length of the space vector for which all three phase voltages are sinusoidal? It is the radius of the encircling circle, okay. So that is nothing but VDC into cos 30, where VDC is the side of or length of the each side of the hexagon. So the maximum value of Vs for which all three phase voltages are sinusoidal is root 3 by 2 into Vdc. Now what is the peak value of the phase voltage that we can get in space vector PWM technique? See, while transforming or while determining Vx and Vy, we found that Vx is equal to 3 by 2 into Van, that I have derived in my last class. So Vx is 3 by 2 into Van, so therefore Van is 2 by 3 into Vx. And for 0, 0, 1, in other words, only upper switch of phase A is on. At that time, y-axis component is 0 and Vs is Vx itself. And for 0, 0, 1, we found that Vbn and Vcn are equal and both are negative. Okay. When Vbn and Vcn both are negative and they are equal, at that time phase A is at the peak. In other words, Van is at the peak. Okay. So I will substitute, see here. So for 0, 0, 1, Vs is equal to Vx, okay, and therefore Van is equal to 2 by 3 into Vs. Okay. And this maximum value of Vs is nothing but root 3 by 2 into Vdc. So I will substitute in this equation. So I will get the peak of the fundamental component of Van is 0.577 times Vdc. Okay. So if I take the ratio of the peak of the fundamental component of the phase voltage that is obtained using space vector PWM technique to the peak of the fundamental component of the phase voltage that is obtained using 180 degree conduction, okay, we found that this value is 0.907 or 90.7%. And for sine triangle PWM technique, this is 78.5%. So space vector PWM technique gives higher value of the peak of the phase voltage, and we found that these peak values is the same for third harmonic injected PWM technique. So in other words, space vector PWM technique is same as third harmonic injected PWM technique. Okay. And how about the number of samples per cycle? I told you that all the sectors should be equally used. All the 6 sectors should be equally used, and samples should be positioned symmetrically about the each sector. In one sector, samples should be positioned symmetrically with one sample at the center. Remember, only then I get the features which I told you in the beginning of my PWM lecture class, the 4 qualities a good PWM technique should have: quarter wave symmetry, no subharmonics, then 3-phase symmetry, at any given time only one switch should switch. Okay. So for that n should be odd multiple of 3. So if there are 3 samples in one sector, they should be positioned at alpha is equal to 10, 30 and 50. Okay. So in all the voltage controlled PWM techniques, say sine triangle, space vector, third harmonic, harmonic elimination PWM technique, the switching frequency of the inverter remains constant. Okay. The rate at which you switch the inverter devices, say in sine triangle, what is the rate at which you switch the inverter devices? It is same as the frequency of the triangle. When the triangular wave crosses the sine wave, you switch the device, switch on the device, and when it cuts back, you switch off. Okay. So the rate at which the inverter devices are switched in sine triangle is determined by the frequency of the triangular wave. So if I keep the frequency of the sine triangle constant, the switching frequency of the inverter remains constant. Is that okay? And it is independent of the type of load. What load it is driving, it doesn't matter. I have kept the frequency of the sine wave, frequency of the triangular wave constant. Similarly, in space vector PWM technique, having fixed the number of samples in one sector, the switching frequency is fixed. Okay. Even in harmonic elimination, we have predetermined notches. So at any given supply frequency, if there are say n number of switchings per quarter cycle, the switching frequency also remains constant. So in other words, the PWM techniques that we have studied so far, the rate at which you switch the inverter devices is constant, independent of the load variation, independent of the supply variation. Okay. Now, what about the current controlled PWM technique? I told you current is controlled within a hysteresis band, and the switching frequency is a function of the hysteresis band. Smaller the hysteresis band, higher is the switching frequency, but then the current waveform, the current drawn by the load, it's approximately a sine wave. A superior sine wave will I get if the hysteresis band is very small. So as you increase the height of the hysteresis window, your switching frequency comes down, but then the quality of the waveform deteriorates. See, in the last class I also told you that we are controlling the current, okay, and the switch is kept on till, or say the upper switch is kept on till the current touches the upper band. See here, at this point the upper switch is closed, current increases, okay, until it touches the upper band, the upper switch remains closed. See, in my last class I might have told you that this technique is insensitive to the fluctuation in the DC link voltage. Why did I tell you? is because we are keeping the switch closed till the current touches the upper band or lower band. So even if the supply voltage changes or input voltage to the inverter varies or fluctuates, it is not going to affect the current waveform. Whereas in all the voltage controlled PWM techniques, in case if you are not monitoring the input voltage to the inverter, okay, flux level in the load may change. You may be keeping V by F constant. This V is proportional to the input voltage of the inverter. Okay. So there is no information available for the PWM controller that the voltage has changed, the input voltage has changed, because this rectified DC has been obtained from rectifying the input AC, 3-phase AC. So if 3-phase AC fluctuates, the DC link voltage also fluctuates. So, and if you have programmed one V by F curve, okay, so flux in the load may change. Now in the last class I told you it appears as if current control PWM technique has an edge over the voltage control PWM techniques, because if the input voltage fluctuates, my current waveform does not get deteriorated in current control PWM technique, whereas my flux level changes in a voltage controlled PWM techniques. But today I am going to tell you that if the voltage fluctuates, the switching frequency of the inverter changes. Okay, see for example, see this is the equivalent circuit. Okay, depending upon the conducting state of the switch, I determine the phase voltage. Okay, I am neglecting the resistance. This is the inductance, and I am assuming that there is another voltage source here equivalent to the induced EMF. This is something the per phase equivalent circuit of an induction machine maybe. Now what is I? VIN minus EIN divided by L is equal to di by dt. Rate of change of current is difference in these two voltages divided by L. Please, VIN and EIN, they are not in phase. Okay. So if the input voltage to the inverter fluctuates, VIN is going to change. So if VIN changes, di by dt will change. So therefore the switching frequency changes, because we are keeping the switch closed till the current touches either the upper band or the lower band. Okay. So therefore in hysteresis current control PWM technique, switching frequency will vary as the input voltage changes. Okay. Again, when the load has reduced, in other words magnitude of the reference current has come down, your switching frequency will again change. See in this figure, EIN has not changed, but the magnitude of current that is flowing has changed. So in other words, magnitude of I ref has changed. Okay. As this current comes down, okay, the rate at which you switch the inverter also changes. So therefore, in hysteresis current control PWM technique, switching frequency varies. So what? The switching frequency of the inverter changes. See, I told you that the frequency of the predominant harmonic that is present in the output voltage is approximately equal to the switching frequency of the converter. Okay. So if the switching frequency itself is changing, the frequency of the predominant harmonic changes. So therefore, if you have to design a filter to eliminate this high frequency component, the filter design is going to be difficult. So that's about PWM techniques. See, so far we discussed about a voltage source inverter, and we have taken the center point in the DC link as a reference, VDC by 2, VDC by 2, and when the upper switch is on, the pole voltage is either plus or minus VDC by 2. So in line to line voltage waveform, in the positive half there is 0 and plus VDC, and in the negative half 0 and minus VDC. Okay. Of course, you may have transitions in the line voltage from plus VDC to minus VDC, that depending upon the inverter switching. So invariably a good PWM technique should have in the positive of 0 and plus VDC. Now there is another class of inverters, what is known as the multi-level inverter. Multi-level inverter. What are these multi-level inverters? See, in the so-called half bridge inverter, potential of A with respect to O is plus or minus VDC by 2, or potential of A with respect to X is VDC. Okay, if I close this switch, this point gets connected here, so VAX is VDC itself, or if I close this switch, this point gets connected to this point, so VAX is 0. I told you that as the power level increases, the magnitude of DC link voltage may also change. See, there are 415 volt motors, 3-phase induction machine. There are 1.1 kV 3-phase induction machine. There are 3.3 kV induction machines, 6.6 kV induction machines. So as the power level increases, the supply voltage to the machines also may increase. In fact, it increases. So therefore DC link voltage also goes on increasing. Okay. As the power level increases, I told you that switching frequency also decreases, it comes down. You cannot switch at high power levels at a very high frequency. Okay. Now I said line to line voltage has in the positive of 0 to VDC. I can say that it is a 2-level waveform. by 0 and plus VDC. Or pole voltage is also either plus VDC by 2 or minus VDC by 2. Can I have more number of levels instead of having 2? Okay. See, at that time VIN now may have large number of steps. Large number of steps. So, as the number of steps increases, have approximate a sine wave. So, the inverters which produces such a phase voltage waveform, they are known as multi-level inverters. I'll just give an example. See here. There are 4 switches, okay, and maybe 6 diodes, okay, and a center type of or center point is connected to again these 2 diodes. How does it work? I close only S1 and S2. So, what is the potential of A with respect to X? It is entire VDC, because when S1, S2 are closed, this point gets connected to this bus. So, it is VDC. When S3, S4 are closed, of course, these 2 are open now, S1, S2 are open, S3, S4 are closed, potential of A with respect to X is 0. VAX is 0, which is same as that we got in off bridge. Now I will close only S2, S3. I will close only S2, S3. So what is the potential of A with respect to X? See here, A, S3 is closed, okay, this point, this, A, this, it is VDC by 2. So, in this case, VDIX is either 0 or VDC. In this case, I have VIX is VDC 0 or VDC by 2. Now there are, so it is a 3-level waveform here. So as the number of switches increases, okay, I can have more levels at the point A with respect to X. Okay. So I have an approximate sinusoid voltage waveform. Okay. So this is the inverters belonging to this class are known as multi-level inverters. Generally, they are popular in high power applications. Okay. I will not go into detail about the multi-level inverters. Slightly an advanced topic. I just told you what is a multi-level inverter. There are literature available on this multi-level inverters. The things are being covered in IEEE papers. Those who are interested, I would suggest that they can read these papers. Okay. Now, let me discuss some of the issues in the voltage source inverter. Okay. What are they? See, a general purpose AC to DC and DC to AC converter configuration. Okay. A general purpose power circuit configuration of a AC drive. In the sense, I am connecting a AC machine here. Okay, this DC is being obtained by rectifying a 3-phase utility supply, uncontrolled rectification. Now the question is, how do I charge this DC link? At t is equal to 0, assume that capacitor is completely discharged. Okay, so capacitor voltage cannot change instantaneously, and you have energized the uncontrolled bridge. Capacitor voltage cannot change instantaneously. Input uncontrolled bridge has been energized. 3-phase supply. So what is the equivalent circuit here? See, there is a voltage source here. Magnitude is, the peak of the voltage at this point is peak of the line to line itself. Okay, and there is a short circuit here. So in other words, there is a dead short circuit at the output of the diode bridge. There is a dead short circuit. Okay, so a large current will flow and it will damage the bridge or the diodes. So therefore I need to regulate or need to control the charging current, or you need to control the rate at which the capacitor is charging now. So how do I do? So there are two ways. Either you connect a resistor in the DC link, okay, or you connect an inductor, a large inductor. Now if I connect a resistor and if I leave this permanently, there is going to be a I2R losses. Okay. So what is generally done is, capacitor is charged through this resistor, okay, and when the capacitor voltage has attained, say, approximately 80 to 90% or so, 90% of the rated, you close the contactor switch or bypass this resistor. Okay, so thereby you limit the charging current and protect this diode bridge. Okay, so this is about charging the capacitor. Now, how do I handle the energy that is being fed back to the source? Source is to the DC link. See, I told you, voltage source inverter is a 2-quadrant converter. Why 2-quadrant? Voltage cannot change, input voltage cannot change polarity, but then current can reverse. There are freewheeling diodes, or diodes are connected in anti-parallel. So current can flow in the positive direction as well as in the negative direction. And in case the power is being fed back by the load to the DC link through this anti-parallel diodes, the capacitor, DC link capacitor, charges because it is receiving energy from the load. So if the capacitor voltage increases, the voltage stress on the inverter devices also increases, because this voltage or input voltage of the inverter should be blocked by this inverter devices. So in this circuit, when this switch is closed, voltage across the switch, this switch is VDC. Okay, so this switch should block the entire VDC here. So if this voltage itself is changing, the maximum voltage at which this switch should block also increases. So in other words, as the DC link voltage increases, the stress on the inverter device also increases. So you cannot allow the DC link to increase above a rated value. How do you do this? So what is being done is, this VDC is sensed, okay, and the moment it increases above a set value, okay, close this S. This switch is closed. So what happens? Now the capacitor discharge, or this energy, the additional energy that is got or received from the load is dissipated as heat in this resistor. So sense VDC, the moment it crosses the set value, close this, dissipate the energy in the resistor, and when it falls below a certain value, open S. Open S. Okay. Now, what is the problem at the input stage? Input stage, we have an uncontrolled rectifier, and at the output of this uncontrolled rectifier there is a capacitor filter. You could have a LC filter also. Now assuming that there is only a capacitor connected at the output of the diode bridge, how does the source current waveform look like? See here, this dotted waveform is the uncontrolled rectification, a three-phase fully bridged uncontrolled rectification, each of 60-degree duration. Okay, the peak is 1.73 per unit. I have taken the peak of the phase voltage is 1. So we have drawn this waveform is 1.73 and minimum is 1.5. Okay, and at steady state, that's how the capacitor voltage will change. Okay, so this is of 60-degree duration, and each device can conduct for 120 degrees in a three-phase full bridge. Okay, so D1, or the diode which is connected to phase A, conducts for very short duration. See here and here. Okay, see these are of 60 degrees, so very small duration they conduct. So basically the power factor, source power factor, is very poor. Okay, so there are going to be predominant harmonics. What is another limitation? As the input voltage to the diode bridge changes, DC link voltage also will change. Now assume that the inverter is feeding a high HP machine. Okay, the moment I am saying high power drive, I would expect that there should be a regeneration from the machine to the source. Okay, or it should be possible to feed back the energy during regenerative braking from load to the source, or in other words, regenerative braking should be possible. Voltage source inverter is a two-quadrant inverter. Current can reverse. So during regenerative braking, load supplies the energy to the DC link. and from the DC link power cannot be fed back because of we have a uncontrolled bridge. Okay. That's why we are dissipating that energy using that resistor. So what are the limitations in the per circuit configuration that I showed you just now? One is input side power factor is poor. Second, DC link voltage is unregulated. It varies as the input varies. Third, though the load is, or though the voltage source inverter is capable of operating in two quadrants, the energy that is received from the load during regeneration cannot be fed back to the source. Okay. Can we address these limitations? So if I summarize, the features of the input stage should be unity power factor operation, okay, bidirectional power flow capability, and possible to maintain constant DC link voltage. Okay, so these are the features the input stage should have. How will you achieve it? See here, we have studied this converter. We call it as unity power factor converter. I am just showing a single phase case. Single phase case. We have 4 controlled switches with freewheeling diodes. Capacitor voltage. Here center a DC link capacitor and an inverter. So this is nothing but a bidirectional unity power factor converter. Power factor is unity. By controlling the magnitude of the source current, you can maintain the capacitor voltage constant. In other words, if there is a perfect balance, power balance of input as well as the output, capacitor voltage will remain constant, and it is possible. Okay. So you can maintain a constant DC link, power factor is unity, bidirectional power flow is possible now. Bidirectional power flow is possible. So in fact, the same philosophy is used in the inverters supplied by ABB to Indian Railways. The drive or AC drive that is used in Shatabdis and some of the Rajdhani express trains, Rajdhani trains and Shatabdis, they use this philosophy. A unity power factor stage at the input, DC link is controlled, and a VSI. Okay. And it is possible to feed back the power to the source. Okay. So this is about the VSI. Now let me talk about offline UPS or an inverter circuit topology. Okay. Why am I calling offline UPS is the inverter that is used in our homes. The moment AC supply goes, after some time, say after a fraction of a second or so, the inverter comes in. Okay. So that's why I'm calling as an offline UPS. What is the input there? At 12 volts battery. What is the output that is required? It's 230 volts 50 hertz AC. Okay, single phase. And I am assuming that I will use a full bridge, okay, with 4 switches. See here, a full bridge VSI. So at any time 2 switches are conducting. Okay. So at the output, okay, you have when these 2 switches are on, VDC appears, and when these 2 switches are on, it is minus VDC. Okay. See, all this time we had assumed that devices are ideal. Okay, you can assume that because voltage drop across the conducting device could be of the order of say 2 to 2.5 volts depending upon the power level. See here, now input itself is 12 volts, 2 devices are conducting, and assuming that voltage drop across the conducting device is 2 volts, now peak to peak that is available at the output is 16 volts, 8 minus 8. Okay. Output voltage that is required is 230 volts, 50 hertz AC. So one way is you have to step up this voltage using a step up transformer. See here, a low voltage AC that is available here. If I take 2 volts drop across each device, so I will get 0 to 8, 0 to minus 8 here, and at this point we require 230 volts RMS. So this has to be a step up transformer. So voltage rating is very low, definitely current is high. Now 8 volts is being applied to the primary winding. Okay. Now this winding has its own resistance and leakage inductance. So there is a relationship between voltages at the 2 ends of the transformer. E1 divided by E2, it is E1 divided by E2 is equal to T1 divided by T2. See here, it is E1 by E2 is equal to T1 by T2 turns ratio, is not this voltage. Now since this is 8 volts and current that is flowing is relatively high compared to the current that is flowing in this side, I'll assume that a 1 volt is being dropped in this. Could be a conservative figure. Okay, could be a conservative figure. So voltage at this point available is 7 volts or so, 7 volts. Okay. But then you require at this point 230 volt 50 hertz AC. Okay. Now if I use a square wave operation, or if the device are on for 180 degree, the peak of the fundamental is 4 by pi into VDC. Okay, see here, I have if I take 180 degree conduction, this is VDC, the peak of this is 4 by pi into VDC. And if you want a pulse width modulated inverter, because square wave has a higher frequency components, in the single phase case 3, 5, 7 all odd harmonics. In case if you want a pure sinusoid, definitely you need to go for a PWM technique, and if I use sine triangle PWM technique, what is the peak using a sine triangle PWM technique? It is VDC itself. For modulation index is equal to 1. For modulation index is equal to 1, okay, the peak of the sine wave is the input voltage itself. Okay, please, in half bridge I said it is VDC by 2. Okay, in a full bridge it is VDC. So peak of this voltage, I am neglecting the drop here, you require 230 into root 2 here. So 230 into root 2 is the voltage that is required here. I am assuming that this voltage will appear here, neglecting this drop. So what is the turns ratio? 7 here, 230 into root 2 is somewhere here. So turns ratio of the order of 47. Okay. And what is the fundamental frequency that is being applied here? You want a 50 hertz supply. Okay. So frequency of the fundamental component seen by the transformer is 50 hertz. Okay. So see, if I write the equation, the VA rating 4.44 into F into phi m into N1 into I1. This is the RMS value of the voltage induced, E1. Okay. F is 50 hertz. So for the same VA rating, as the frequency of operation increases, size comes down. I hope you all know this. As the frequency of the operation increases, size of the magnetics comes down. But then here, the frequency of the fundamental component is 50 hertz, so you require a 50 hertz transformer. So that is the reason the inverter that is used in our home is very heavy, because there is a 50 hertz transformer. Now can I try to reduce the size of the transformer, thereby reducing the overall weight? Definitely it cannot be used if I take this philosophy. What is the philosophy? We had a low voltage DC, we inverted it, I got still a low voltage AC, then we used a step up transformer and boosted this voltage. Now instead of stepping up the AC voltage, can I step up the DC voltage? I will repeat, we did DC to AC, okay, low voltage AC, and again use a step up transformer, increase the voltage to a required value. Now instead, can you boost the DC voltage itself? See, we have studied various classes of DC to DC converters, with transformer, without transformer. There is a boost converter. I told you that maximum ratio could be of the order of 10 to 11 or 10 to 12. Then we use the transformer, flyback, forward, and push pull. Okay. So using a transformer and a DC to DC converter, I can boost up this 12 volt DC to a relatively higher voltage DC. then you invert this high voltage DC to high voltage AC. High voltage in the sense 230 into root 2 AC using a PWM technique. So something like this. Low voltage DC 12 volts, a DC to DC converter, of course using a transformer. Okay. Now what sort of a transformer? It is a high frequency transformer. This transformer that is used in push pull, transformer that is used in forward. Okay. These are high frequency transformers. So size comes down. Size comes down. So here I have a high voltage DC. So if I just invert it, I should be able to get a peak value which is equal to 230 into root 2. So the overall size of this inverter reduces, weight reduces, is elegant, because we are not using a 50 hertz transformer. There is a transformer, okay, in a DC to DC converter that is being operated at a much higher frequency. But then only disadvantage here is there is no isolation between the load and the inverter. There is no isolation between the load and the inverter. Okay. More about it we will see it in the next class. Thank you.